Hello everyone and welcome to this lecture in the hands-on large language models series. Today we are going to start a new topic which is called as creating text embedding models. In the previous set of lectures we have used text embeddings and image embeddings for a wide range of tasks, but until this point we have not really seen how do we create embeddings of texts. So let's say, for example, if you have a text such as this is a cat, and if you want to take this text and convert it into a vector in a higher dimensional space, let's say if you want to convert it into a 384 dimensional vector, how do we do this such that this vector for this is a cat and let's say kitten, or let's say my cat is hurt, I want to convert all of these into text embeddings such that their vectors lie close to each other because they are semantically similar. So if let's say this is the vector 1 for the first sentence, this is a cat, this is a vector 2 for the second sentence, and this is a vector 3. I want v1, v2 and v3 to lie closer to each other in the vector space. I am just showing a two-dimensional space here right now for the sake of simplicity, but in higher dimensional vector spaces also I want these vectors to be closer to each other. Now what is close and what is far in a vector space? There are usually different metrics to find the distance between vectors. It can be a Euclidean metric or it can be cosine similarity. We are not going to discuss about the distance here, but we are mainly going to discuss how to go from a text and take it into a vector such that the meaning is preserved with respect to other sentences. And this kind of thinking applies to images as well. So today we are going to discuss about one method especially, and that method is called as contrastive learning. Contrastive learning is a method which takes text or images and it helps us to convert these text or images into embedding vectors such that the meaning is preserved. And the first paper for contrastive learning actually came out in 2005. So the paper is titled Learning a Similarity Metric Discriminatively with Application to Face Verification. So the first applications of contrastive learning, I believe, was with respect to faces. So this paper has more than 5,000 citations now, and Jan LeCun was one author on this paper. Then in 2013, there was another model which is pretty popular and many of you might be knowing it. That is the word-to-vec model which Google used. And I believe that they also used contrastive learning for constructing this word-to-vec embeddings. So this is a bit of history about contrastive learning, but this is a very powerful method for creating text embedding models. So first let us try to revise a bit regarding what is a text embedding model and why do we really need those. All of the lecture material which I am showing right now, the images, etc., they are taken from this book, Hands-on Large Language Models, which has been written by J. Alamar and Martin Grutendorst, and it's published by O'Reilly. So I just wanted to provide this citation and reference at the start of this lecture. Okay, so the reason we need embedding is that we need to convert textual data into numerical representation. So when you say my cat is sick, that's the text, right? But when we feed this to a computer, we need to feed it in the format of a numerical representation. And that's the reason why we need embedding models in the first place. So the process of converting data, which can be text or images, into numerical representation is called as embedding. And that's when we have text embedding models and image embedding models. So let me repeat this again. The process of converting data, which can be text or image, into numerical representations is called as embedding. Okay, so here is an image which again has been taken from the book Hands-on Large Language Models. And what has been shown here is that you have a textual input, let's say a piece of text or multiple sentences, and you want to take those and convert it into a numerical representation. What you use for that conversion is something which is called as an embedding model. So as has been written over here, we use an embedding model to convert textual input such as documents, sentences and phrases into numerical representations which are called as embeddings. So for the sake of simplicity right now, just remember that embeddings are nothing but numerical representations. So then you might be thinking, okay, I can just take sentences and convert it into random vectors, right? What is a good embedding and what is a bad embedding, and how to distinguish between good versus bad embedding. The main challenge comes from the fact that good embeddings are the one which capture the semantic nature or the meaning of documents. So as I mentioned over here, documents or sentences which have a similar meaning need to lie closer to each other in the vector space. And embeddings which make that possible, they are said to be good embeddings. Whereas embeddings in which similar documents are far apart in the vector space and dissimilar documents are closer to each other in the vector space, they are not good embedding models. So here are the two characteristics of good embeddings. The first characteristic is that vectors of similar documents need to be similar or closer to each other, and vectors of dissimilar documents need to be dissimilar, so they can be farther apart from each other. And let's take an example which has been shown in the Hands-on Large Language Models book. So here you can see that this is the vector embedding for this acne cream cleared my skin and this horrible lotion aggravated my breakouts. These two sentences kind of mean similar things, right? They are with respect to facial uh, cleaners and their effect on the facial, let's say, skin tone. So that's why those are similar and closer to each other in the vector space. Now let's look at these two sentences. This vacuum cleans efficiently is the first sentence, and the second sentence is the weak suction left dirt behind. These two are also, they mean similar things, and that's why they are closer to each other in the vector space. And finally, the last two sentences are my order was late and extremely fast shipping. Both of these sentences talk about orders, talk about shipping, and that's why they are closer in the vector space. So the idea of semantic similarity is that we expect textual data with similar meanings to be closer to each other in a higher dimensional space. That's the whole idea. Now, in addition to semantic similarity, embedding models can also be trained for wide range of purposes such as sentiment similarity. What is sentiment similarity? The same embeddings which are shown in this figure can also be classified a bit separately, right? So these three are kind of like a positive sentiment. The vacuum cleans efficiently, this acne cream cleared my skin, and extremely fast shipping. This is a positive sentiment. So this is one group. Whereas the suction left dirt behind, then it aggravated my breakouts and my order was late. This is a negative sentiment. So they are all clustered together in one space. So embedding models can be trained not only to capture semantic similarity, like how we have shown in this figure, but they can also be trained to capture sentiment similarity, like how it has been shown in this figure. So let's say positive sentiment vectors are all in one place and negative sentiment vectors are all in one place. So by presenting the model with enough examples of semantically similar documents, we can steer towards semantics, whereas using examples of sentiment would steer it in that direction. So all of it depends really on the training data which we have and what is our objective during training. If the training objective is to make semantically similar documents closer, we will achieve something like this. Whereas if the training objective is to make sentiment documents with similar sentiment closer, then we will achieve something like this. So that's the difference. Okay, now that we have understood what is the meaning of embedding models and what characterizes good embedding models and what characterizes bad embedding models, we can now come to the next part, which is the main purpose of today's lecture, which is understanding about contrastive learning. So contrastive learning, as I mentioned, the technique has been around since 2005, which is around 20 years back. But since text embedding models became popular, researchers realized that the same process of contrastive learning, which was applied for images, can also be applied for training and fine tuning text embedding models. So this is now really a major technique for creating these models. So remember this schematic which I showed you. There is a textual input which goes through an embedding model and then there is an output. The way these models are developed, contrastive learning is a technique which helps development of such models, such embedding models, which we are going to learn about today. Okay, what's the aim of this technique? The aim of this technique is pretty simple. We need to train an embedding model such that similar documents are closer in a vector space while dissimilar documents are farther apart in vector space. So for this we need a training objective. We need a training objective and we need loss function. Once we have the training objective and the loss function, we can do gradient based optimization methods to minimize the loss function so that our objective is attained. And what's the training objective for the case of contrastive learning? It's two things. First, so the training objective in contrastive learning is two things. The first training objective is to make sure or to minimize the loss between similar documents. And you might be thinking, that's it, right? If I do this, then I'll have a good embedding. But that's not usually the case. You also have to maximize the loss. You also have to maximize the loss between dissimilar documents. And contrastive learning aims to do both of these two at the same time. So we should not just stop at minimizing the loss between similar documents. We also need to make sure that our embedding models have a very high loss for dissimilar documents, which will make sure that dissimilar documents never come closer to each other. So that's why it's extremely important that these two things are achieved for us. Somehow similar documents should be closer and there is a loss on that, and dissimilar documents should be farther apart and there is a loss on that also, and both of these loss functions are actually added to get or to achieve our training objective. That's the main idea behind contrastive learning. That's why it's called contrast. If we were just minimizing the loss between similar documents, the name would be different. It would just be like a normal training procedure which we have in neural networks, let's say. But the novelty here comes from the fact that we are also maximizing the loss between dissimilar documents. So here you see we have minimize and maximize in the same training objective, and that's why it's called as contrastive learning. Now you might be thinking that why can't we just do one of this? Why can't we just minimize the loss between similar documents and just stop over there? So to give you an intuition of why contrast is so important, let's take a practical example. Let's say you have a robbery which has happened in the bank and you ask the person that, hey, why did you rob a bank? And then the robber might say that because that's where the money is. But this is not what we wanted, right? From the question, we wanted to ask the robber, what is your main intent of robbing? Why are you robbing? What has happened in your life so that you are starting to rob things now? We want to get information about why the robber does this action of robbery. But instead, the only answer we have got is because that's where the money is. And the reason why we have got this answer is because we have not provided the question in a correct manner. Now let's say instead of asking why did you rob a bank, we add a bit of contrast in the question. So let's say we ask the question as, why did you rob a bank instead of obeying the law? So if the question is, why did you rob a bank instead of obeying the law? Then the robber may answer something like, because I am poor and I needed quick money. Now this is the answer which we really expected, right? And the only reason why we got this better answer is because we posed the question as a contrast. So when we use contrastive learning, or when we ask questions as contrast, we often get more information than if we just ask the question as it is. Let me give you another example which is a bit more visual. So let's say a kid is there and they see a horse, and if you ask the kid, why is this a horse? The kid may say that it has four legs, it has a tail, it has fur, etc., and it runs very fast. Now, these answers are correct, but with these same answers, it could also be a zebra, right? Because a zebra also has four legs, tail, fur, and it runs very fast. So essentially, the answer given by the kid is factually correct, but it can be even confused for a zebra. Instead, if you ask, why is this a horse and not a zebra? That's when the kid will be forced to think of a horse. The kid will be forced to think of a zebra, and then try to think what differs the two. And then the kid may say that a horse has no stripes, or a horse has a longer mane than a zebra, or a horse has a shorter ear length as compared to a zebra. So when we feed an embedding model different contrasts, it starts to learn what makes things different from one another. So essentially, when you pose questions as a contrast, the kid here can really start to understand what makes a horse and a zebra different from each other, right? This is very similar in the case of embedding models. We need to make sure similar documents are closer, but we also need to make sure dissimilar documents are farther. We need to give a contrast when training. We can show similar images, but we need to show dissimilar images also. And when we show similar as well as dissimilar images, the embedding model starts to learn what makes things different from one another, and that is why it starts to understand the distinctive characteristics of concepts. So by providing the contrast between the two concepts, the model starts to learn the features that define the concept, but also the features which are not related. That is very important. We should know what defines a particular image or a particular text, but we should also know the features which are not really relevant, right? So whereas let's say if you have a cat and dog, you should know the features which a cat has, but you should also know what are the features which makes it which are not relevant for a cat, right? Like maybe a cat does not have flappy ears, or a cat does not have rounded eyes as much as a dog does. So you need to, when you train the model, you don't just need to say that, you don't need to give it similar images to a cat, you also need to give dissimilar images, so that the model knows what the cat is not, or which features of a cat are not really important. So the whole idea of contrast is that we get more information when we frame the question as a contrast. That's the most important thing which I want to convey in this lecture, is that if you just pose a question like, why did you rob a bank, or why is this a horse, you get some information. But if you pose the question as a contrast, for example, why did you rob a bank instead of obeying the law, or why is this a horse and not a zebra, you get much more information than if you just pose a single question. So contrastive learning, even if you forget everything, let's say, which I've taught you in this lecture, the only thing which you can remember is that contrastive learning helps us get more information. And this is something which you can see in your day-to-day life also. When you interact with people, if you want to get more information, just try to ask the question in the form of a contrast instead of just asking the question directly. So this is the main intuition behind contrastive learning itself. And I have found a very nice article which I'll also share with you, which explains contrastive learning a bit more visually. Okay, so now let's say that so when you do contrastive learning, now you have understood the objective, right? Now let's talk a bit about the loss function. So when you do contrastive learning, you have something called as an anchor image. You have something called as an anchor image, and then you have positive, or I should say anchor text or image, anchor text or image, and then based with respect to this anchor, you have positive examples and you have negative examples. So let's say we have the anchor image as that of a raccoon. That's why it's called IA here, which is anchor. So the anchor image is of that of a raccoon. The positive examples, which means the examples which are related to this, can be other examples or other images of a raccoon, or it can be the same image but augmented, which means rotated, or the brightness can be changed, or some parts of that image can be clipped. But essentially, the positive examples will be all other types of images which are related to the raccoon, and the negative examples will be all other images of other animals because they are not related to the anchor image. So as you can see, this is the anchor image, right? Now I plus, which is the positive image, that is that of another raccoon, and I negative is that of a negative image, which is that of another animal. So the first thing which you do is first you take all these, you take the anchor image and you project it into an embedding space. Nothing is optimized yet, but initially we start out randomly. Then you take the images which are classified as positive with respect to the anchor, and then you project them. You take the images which are classified as negative with respect to the anchor, which are all other images which do not look like a raccoon, and you project them. And your whole aim is that you need to minimize this distance d plus, because the positive points need to be as close to the anchor as possible, and you need to maximize this distance d minus, which means the negative point should be as far away from the anchor as possible. So you need to maximize d minus and you need to minimize d plus. That's your whole objective, and during the training process, and that's how the loss function is defined. Now, to define the loss function, so now here is another example. See, you have an anchor. So the anchor is that of a dog. To get the positive image, you don't take any new image from the data set, but you just add a color gradient to this dog. You can even rotate the image a bit. That's your positive image. And the negative image is that of a bird, let's say an owl. You project all of this and you get vectors, and then you minimize the distance between the anchor and the positive, and you maximize the distance between the anchor and the negative, and that's what defines your loss function. So the loss function also can be of multiple types. The simplest loss function is the contrastive loss, which again was introduced in this paper, 2005 paper. In this contrastive loss, what you're doing actually is that you start with one image, let's say the anchor image, and then you take any other image. If that image is positive with respect to the anchor, then you minimize the loss like what we saw right now. And if that image is negative with respect to the anchor, you maximize the loss. That's what's written over here. This is called as the contrastive loss. In contrastive loss, you just take two samples at the same time, two images or two text. The second type of loss is called as a triplet loss, where in this loss you take three things at the same time. So you take the anchor, you take a positive image with respect to the anchor, and you take the negative image with respect to the anchor. And in the same loss function, you minimize the distance between the anchor and the positive, and you maximize the distance between the anchor and the negative. So what is the difference between the contrastive loss and the triplet loss? In triplet loss, you are actually taking three images at the same time into the loss function, whereas in the contrastive loss, you are only taking two images at the same time into the loss function. And then there are multiple other types of loss which were proposed later, such as lifted structured loss. Then there is also n pair loss, where instead of triplet, why don't we have more negatives? Or let's say instead of one anchor, one negative and one positive, in triplet loss, what was proposed is we can have one positive and multiple negative examples. Whereas in triplet loss, we just have one negative, right? In n pair loss, we can have 5, 10, even more negative examples. I'll share the papers for all of these type of losses so that you can take a look. Then other types of losses are noise contrastive estimation loss, the info NCE loss, soft nearest neighbors loss. There are various types of losses, but this is the loss function. And the whole goal of all of these loss function is the same. We need to make sure that the positives with respect to the anchor are closer in the vector space and the negatives with respect to the anchor are farther apart in the vector space. So during training, what is done is that we have images or we have text, and this loss function is applied to all of this data, and we try to achieve the training objective. And at the end of it, we have an image or a text embedding model which takes input as text or image and converts it into an embedding which preserves the semantic similarity, or it preserves the semantic meaning. Now, one advantage of this contrastive learning is that the amount of training data which you need is actually not that much. Because if you look at the original paper of contrastive learning, the way they constructed the training data is from the same image itself. So if you have one image of this person, etc., like this, you can rotate the image, you can add noise, you can remove certain parts of the same image. So then that belongs to the positive class with respect to the anchor, and with respect to the negative class, you can take all the other images. So even if you have small image or even if you have less amount of training data, you can in an effect have a much larger training data set if you just do augmentation with respect to rotation of the image, transformation, changing the brightness, contrast, etc. So that's what's being done here actually. If you see, this one image has been augmented, and this pair here which I'm showing right now, that's a negative, and what the image which I'm showing right now, that's a positive, because they are from the same class. And the same technique can actually be used. So if you see the paper, when they started this paper, they said that they introduced this method where the number of categories is very large and not known during training, and where the number of training samples for a single category is very small. So even if the training data is not labeled, it still works for you, right? How? Because just take one image, let's say that is your anchor image, augment that image through rotations, transformations, brightness, contrast, etc. All of that will be positive with respect to this anchor, and all others will be negative with respect to this anchor. So you don't even need any labeling to be done. So that is another advantage of contrastive learning. Okay, so this brings us to the end of today's lecture, where we learnt about contrastive learning, and that can be a very useful and an important technique to create text embedding models. There were several references which I showed in today's lecture. The first is this hands-on large language model book and the repository. I'll share the link to that. The second is this blog on contrastive learning. These two blogs actually, I'll share those as well. And finally, this paper which was introduced in 2005. Thanks so much, everyone. I hope you are liking these lectures. In the next set of lectures, we'll start looking at other ways of creating embedding models, such as SBERT or sentence BERT, how to use sentence transformers. And then we'll actually train an embedding model in Google Colab. So currently we are just looking at theory so that your theoretical understanding is strong. Then we'll actually look at code in Google Colab and train an embedding model fully from scratch. So thanks everyone, and I look forward to seeing you in the next lecture.